Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. In this lesson, we're going to be deriving the Gibbs-Duhem equation. So in the last lesson, we saw that we can define a partial molar quantity for a property that is indicated as M with an overbar. It is the change of the extensive quantity for M as you change the number of moles of one species. And the intensive property for the mixture is going to be the mole fraction times the partial molar property of that species, and you add this up for all of the species. Now, M could be any of our energy functions, or the volume, or the entropy. We also, at that time, introduced a property change of mixing. And the property change of mixing is this actual quantity for the mixture minus what you would get if you had just taken the pure species specific quantities for M. In this lesson, what we'll be doing is looking at how we can combine these and use this to eventually simplify our discussion of mixtures. So let's see about how we can use these partial molar properties. Now we know that the extensive quantity M is the number of moles times the intensive version of M. And if I wanted to look at the differential of that, a la a fundamental relation, and I was going to go with M as a function of temperature, pressure, and moles of each of my C components, then I would say that dm is N times the number of moles, how that changes with temperature, times dt, plus the number of moles times how M changes with pressure, times dp, plus the number of moles times how M changes with changing number of one specific component's moles. And that's my partial molar quantity. And so we end up with a fundamental relation that can be written as this top expression here. Now, the number of moles of a particular species here really is the mole fraction times the total number of moles. And so this dNi could be rewritten as xidn plus n dx, simply using a product rule from calculus. And so if I introduce this into my fundamental relation form up here, I have the change with T dt, the change with P dp, plus the partial molar properties times xidn plus n dxi. Of course, I could have at the beginning said, wait a minute, I'm looking at dm. M is N times intensive M, and I could have applied a product rule to this. Okay? So if I do this, I'm going to end up with this is equal to this. I have pieces with dn's everywhere, and I have pieces that are multiplied by n. If I group all the things that had an n multiplied by them, and I group all the things that had a dn, I end up with these expressions here. Okay. Pause the tape if you need to look at this a little longer. So if I take that and then use what I know, I have defined that partial molar properties times their mole fractions, when I add them up for all components, that is the intensive M. Here I have that expression, so I could replace this with M, or replace this with this, and I now have that on each side. I can eliminate that. Okay? So we end up now with this simplified piece, okay, where I have these three terms that are left. And so the sum of these, or these two minus that one, is going to identically be 0. And this is what we're going to call the Gibbs-Duhem equation. Now, this is the general form of the Gibbs-Duhem equation, and we're going to be looking at this and one other special case where we fix the pressure and temperature. And if I fix the pressure and temperature, these first two terms will be identically 0, and I'm left with the sum of the xi's times changes in the partial molar properties. They will add up to be 0. And so these are going to be the two forms of the Gibbs-Duhem equation that we will be looking at. In our next lesson, we're going to be looking at how I can apply this in some useful ways. Thank you.